To begin, we'll start with an introduction of myself and Kevin. So Kevin and I are undergraduates at McMaster University, and we are doing our undergrad in material science. We both contribute to this club called the Computational Material Society that is trying to get more students engaged with computational materials, coding concepts, and that sort of thing. So on your end, Mike, could you maybe give a brief background about yourself and the kind of work that you do?
Yeah, we'll go way, way back. So I'm a military brat. So I grew up in many, many different locations. I've basically lived pretty much in every province in Canada, and I spent 4 years in Germany in high school at a Canadian Air Force base that was there. I have been interested in science and innovation and invention since I was probably 4 or 5 years old. I got many little books on how to do little projects, build little apparatus, and so on. Through high school, I went into university, did Dalhousie University. I started in physics, took a break there because I was actually particularly interested in the origins of gravity. That was my driving at the time. But then I decided I was not willing to devote my life to a theory that I may or may not end up answering a question to. After some soul searching, I realized I also had a love of computer science. So I started programming actually when I was about 10 years old on my old Commodore 64. So when I realized that computational physics and computational material science was a really new emerging field at the time, I really went back and I split from a pure physics degree, going from more the quantum stream of physics and started delving more into materials and branched out and did a dual major with computer science in my undergrad. And then I went on to a master's and a PhD at McMaster University, where I was focusing on computational phase transformations, which ties a lot of thermodynamics with kinetic modeling, developing high performance computing algorithms to solve problems and understanding how microstructure and patterns emerge during material phase transformations. And then I went on to University of British Columbia, where I did a 2-year and 1-year postdoc in sequence, 2 years in the physics department, and 1 year in the materials engineering department at University of British Columbia, and then moved to my current position with Natural Resources Canada in the materials technology laboratory, where we develop and study materials for energy applications. And energy applications being broader in that, energy efficiency, as well as energy production, energy transportation. That's basically our general mandate there. I'm also adjunct professor at both McMaster University and the University of British Columbia, and I regularly supervise or collaborate with students and professors at a number of institutions in the country.
Wow, that's awesome. That's a great rundown.
I think that's very interesting. Yeah. Is there like anything in particular for you, Mike, that drew you to the industry? Like, what initially set you down this path of exploring this computational aspect of material science?
I think it's really more of a random walk, where I randomly bounce from opportunity to opportunity, but you're following that gradient down and saying, oh, this is interesting, so I'm going to follow that path. That's interesting. And I don't think there's one instance that ever did it, but I've always had an interest in patterns and problems, and I've always had an interest in computers and making algorithms more efficient. So I think that was the driver. Materials, to me, in a lot of ways, has been secondary to that. Like my predominant has always been in the application and making them efficient. Not to say that I'm not really interested in materials, but that's been more the target area where I'm working, whereas my real interest, core interest, has been developing new ways to do things.
Okay. Just to piggyback off that, so at your current job, what would you say is the most exciting thing, or like the best thing that you think you do at your job currently, and also what do you think is the least likable thing of your current job?
Am I allowed to answer that?
It's
Only if
fine.
you want.
don't
Only
need
if
to.
you
You don't
want.
need to.
Yeah.
It's up to you.
Well, the most interesting thing I think in my current position is it's kind of a balance of the rigor of delivery in industry with the freedom of exploration you might have in academia. Where in academia you have almost complete autonomy to do stuff, assuming you can get funding and students, because you're always driving towards publication. In my job, we're still trying to publish and get data out there, but it's not as much of a drive to get those publications out. What they're more interested in is, okay, what is the impact of what we're doing and how does it support the industry? How does it support our researchers and how does it support our economy and how does it support Canadians in general? So having that kind of freedom, and you can kind of move around within that zone a little bit. You still have to write proposal applications, you still have to be funded and so on, but you do have a little bit more, I think, freedom in what area you're going to move into than you would say in industry, but you are tied a little bit more to direct applications than you might be. Not to say in academia you wouldn't have a direct tie, but sometimes you don't always have that or don't need to have that. And so people drift away from it.
Yeah, for sure. Because I think, at least like I can speak for myself, that I'm currently doing a research co-op at Stalco, and I can say that it's very like rewarding when you see like something new that you've developed is positively impacting society in different ways. So just to move on from that, is there anything exciting you do outside of work?
So I tend to drift from hobby to hobby. So I used to fence.
Wow.
I had some, actually when I was at McMaster, I was on the fencing team there. But then I started having some issues with my wrist. So I stopped that. One day I'd like to actually get back into it because it's a nice sport to have a physical activity. Lately I've been getting into teaching myself piano, and I am doing a lot of sculpting. So I'm sculpting a cement type material. So I don't have to have a kiln to fire anything, it just chemically cures. And then it ties back to my materials interests.
Going first.
Yeah.
I think it's pretty cool, Mike, because I can relate to that a lot, like learning piano at least, because I've actually been studying piano for like the past 9 years, but not in school, but like as a hobby. So like I'll just like I have a piano at home and I'll just like practice. So I think yeah, it's definitely really good. Is there like any kind of piano you're more interested in? Is it like more classical music or any specific kind of music you're looking into?
I don't think there's any specific. I'm still pretty junior, so I'm playing very simple things at this point.
Okay.
But I do like the modern tools where because I bought a digital piano that I can work on, so you can actually connect it to an online tool, and it tracks as your key presses and so on, like to know if your tempo has changed or
Yeah.
staying on key. So it's very useful when you don't, especially during COVID, where you don't necessarily want to go to visit with an instructor who do in-person lessons. You can kind of do it offline and on your own schedule.
Yeah, that's great. Okay, so I'm just gonna pass on to Jeremy to ask you some more industry/work related questions. So yeah.
Yeah. Thanks, Kevin. So
I don't think I answered what was the worst thing that was.
it's the floor is yours if you want. If you want.
Yeah.
It's all good. If you can't say it, we understand.
Yeah.
No, it's more just I guess more recently I've taken on more of a management role, and there's you talk about work-life balance. Well, there's work balance, because your love and your passion is the research, but being in a management role now, you have a lot of administrative duties which come with it, and sometimes those administrative duties can take you away from the thing you want to do.
Oh, for sure. Yeah,
So
that's
so I think that's probably the worst part of the job is when you have to take away and you have to handle all of these administrative tasks and government paperwork and so on.
yeah, and I feel like as you gain more seniority, there's just more. You're far more useful in that managerial role because you have a broader understanding of the whole organization.
Yeah.
For sure.
I know a lot of scientists, professors, industry, government, they have all kind of indicated they would love to just be a postdoc forever. If they could get the security, they would just stay in that role.
Yeah. Yeah. Um, so to ask you some more, I guess, industry and work related questions, maybe you could describe the kinds of things that you do on a standard work day. Like how does the most general schedule look for you on any different week?
First thing every day, a cup of coffee. Yeah.
That's fair.
Most
Yeah,
most important part of my day.
that's right.
Yeah. But yeah, generally nowadays, first thing, my calendar runs my life. So I go in, I look at my calendar, try to see what meetings I might have for that particular day, and then I'll start planning out and say, okay, how big of a time block do I have within that day that isn't devoted to meetings or other administrative tasks? And what of my research objectives that I'm working on can I fit into those blocks? So this is more the life of a manager who is doing research as opposed to somebody who's just predominantly just doing research. So during the day, I will tend to either do, because I'm more of a theoretician, computational focused researcher, and in particular, a lot of my research is developing custom models, custom codes. So my interaction with commercial software is fairly limited. So I try to design, it's really shifted how I design my projects in that I try to become extremely modular. So if I could break down the problem into very small modular chunks, then I could sit down. If I only have an hour and a half between meetings, I'll take maybe 10 or 15 minutes. I got to just to get into the frame of mind and try to tackle that small chunk of programming that I need to do. And then that will subsequently be 3 or 4 more chunks where I have to go back and do the testing on it to make sure that I didn't rush through it and do rigor. So there's a lot more in terms of time management requirements and really compartmentalizing the development. Whereas in the past, when I was doing my postdoc and my PhD, I would do 16, 18-hour programming marathons. I would have a big problem and I would just keep programming until the birds were chirping the next morning, until the task was completed. Whereas now I don't really have that kind of freedom to do that kind of work.
Right, right. And as a follow-up question, like how much of when you're programming something, how much of it as like a percentage is just physically writing it versus all of the maintenance that comes afterwards, would you say?
I'm going to add a component that I think a lot of people leave out, and that is the design phase. So I probably spend about 80% of my time without touching code or syntax, designing a piece of program. And once you get a really good design, and by design, I mean you also go through by hand, walk through what the expected, like almost pseudocode line by line, what's going to happen during that program, and writing down by hand what you expect the output to be. And so then when you go to the coding, and this is a difference between coding while learning versus coding from a design, is once you go to the coding part, you really just run into maybe syntax errors because the design should be fairly solid. Sometimes you run into issues where your design was just flawed. But if you walk through it by hand, you tend to, at least I find, I tend to think more about what each line is doing than if I were just to type it. Because I always found there was a, I don't want to say desire, but a temptation to hit that compile button and just see what happens rather than actually thinking about what it's actually doing. Whereas if it's on paper, you can't do that. And then now I've tended to move away from paper. I actually use a lot of flowcharts to design my objects, what are my functions, what are my procedures, and so on, as the programs get more and more complex.
Yeah. Oh, I know exactly what you mean by just hitting that compile button. A lot of that hits home for sure.
And but then I would say maybe 5% is going to be that syntax development, so actually writing down the code, and then you have to do the rigorous testing. And so there's going to be a lot of rigorous testing. So maybe I'm going with 150%, since I weighted 80% and 5%. But yeah, so you can never underestimate the amount of time it's going to take to do that last visible 10 or 15%. Like I like to call it that it seems like you've done 90% of the work, but that 10% can take as much time as the other 90% because you have to do all the rigor checking, make sure everything's working properly.
Oh, for sure. Well, that's awesome. So I have another question for you, just as like a broader question. If somebody came up to you and asked, so what do you mean by computational material science? How do you think you would respond?
I'm going to have to ask you to ask me that question again.
What is computational material science to you, essentially?
If you had asked me 8 years ago, I immediately would have gone to simulation. So basically doing, you're simulating a process, you're doing finite element simulations, you were running a DFT code. Now I tend to view computational material science is any aspect which is really heavily leveraging computers to perform some sort of task. So this really broadens into the field of artificial intelligence, machine learning, data analytics, even like database design, data management processes, and so on. So all of this really, to me, is the avenue of computational material science. And it's really important now because even 8 years ago, all of these things were pocketed, but now we're really starting to see many more linkages between them. And so each subfield in the area of computational material science really has its own field, and now we're trying to bring them together, and that's really going to be the future of what it's going to look like. And what it will look like exactly, I don't think anybody can really answer, but it will be more about how to link these things together and how to connect it to real problems than it will be in developing one particular subset area.
Interesting. So would you say that computational materials has kind of broadened in a sense over time?
It's certainly broadened in my mind. I think there's probably people doing subsets of this all over, and I don't know if all of them would have even considered themselves computational material science, but I think that's changed with the way technology has evolved, especially with the advent of like cloud computing, and you can get a lot of these database systems, instances in the cloud up and running. You can much more easily access high performance computing systems. In fact, you can get very powerful like desktop computers, which are as powerful as some supercomputers that were used 10, 15, 20 years ago. I used to do a talk when we first got our Cray at the lab where I said that, when the first supercomputer came out, it was as powerful as my iPhone. Well, now 10 years later, our cray is basically antiquated, and a modern desktop is starting to approach, especially if you consider GPU technology, even surpass the compute capacity of our old supercomputer.
Yeah, no, it's staggering, especially with GPUs though. If you can manage to get a handle on one these days.
Well, yes, and well, GPUs are also limited in other aspects in that they are good at some problems, but not so good at others. Whereas a more general purpose compute core, but even those, trying to figure out what I was going to say. A general purpose compute core over 10 years ago is more powerful than it is now, more because of the sub-processors, and the compilers have gotten better, and the caching times have gotten improved, and so on. So there's been a lot of little improvements in the CPU cores that really can add up.
Oh, for sure. Yeah, no, like you said, it's amazing how fast technology advances. Even, myself, I'm only 21 years old, but even from when I was a kid, it's staggering to see having like a little Game Boy handheld to versus essentially what is like a handheld computer and the modern gaming devices. It's just crazy.
Yeah. Well, look at me, I had Commodore 64 kilobyte.
Yeah, no kidding. No kidding. No, that's great. So I'm gonna pass it over to Kevin again to ask some questions for maybe newer people to computational materials, or somebody who's more interested in the field.
Yeah, so just as a starter, as for example, if you could imagine a student who's coming to materials engineering in second year here at McMaster University, and they want to specialize in the computational aspect, what would be like the main advice you would give them? Something that they could do maybe on the side or in school to truly excel in this industry?
If you're gonna do like get really into it, I mean, get really into computational material science, you need to learn how to program. And while you could take courses in programming, that in itself is really, like, it'll give you some of the foundations of it, but you really need to find a project. It's something that you're really interested in, and you don't even have to be, I'm going to say, successful in the project. Simplify it down, start small, kind of build your way up and learn the different components as you go along. One, it's good for your resume too, but two, it really puts perspective of the things you're learning in class, because you're going to learn theories in programming class. You're going to learn about algorithm design, and you're going to learn this thing called big O notation. How does your algorithm scale with in terms of computation? You're going to learn things like data structures. You're going to learn like lists and arrays and dictionaries and so on. But unless you actually look for ways to apply them to something you're interested in, you're going to forget most of it. Another thing to do, and I think one of the most beneficial things I learned in my undergrad, or somebody said to me, is that they're not interested in having us retain a lot of knowledge. Like, yes, we want to learn it, and they're happy if we really learn, say, remember and retain 10% of what we actually are taught. The point is really to learn how to learn. And you're only going to do that if you try to expand beyond what you're taught in the classroom.
Oh yeah, for sure.
Yeah, I think that's great, especially like your first point regarding projects, because I think that's one of the major things, at least like regarding our club currently, is that we try to design projects for new students that they can get their own hands on it, get their hands dirty, and then we give them guidance if they ever get stuck with anything. And even I believe, was it some time last year, Reyes and I, we worked on this one project where we had to like segment phases in steel microstructure using image processing and AI. So it was kind of it was a super fun project because Rain is more on the image processing side of things, and I'm more on the AI side of things. So for example, he would do some preliminary, so he would do some like introduction, some preliminary cleaning of the images, and then I'll do some more of like noise reduction with AI and other stuff. And we definitely learned a lot from like working on our own projects on the side. So yeah, I think that's great. And just moving on, so regarding hard skills, at least you mentioned programming, and I guess you would say it's a soft skill is learning how to learn. But are there any further either soft skills, for example, like working with a group? That's I guess it's common in a lot of places, or are there hard skills that you'd want others want students to be more aware of or be more skilled at in this
Yeah,
field?
one that, well, I think it's probably common to a lot of engineering and science, but particularly now as we're broadening out and there's a lot more moving parts in the computational world, communication. So this could be anything from talking to a person to get across what you're trying to accomplish. What are the problems you're facing? What do you need for inputs and outputs? To documentation. Practice commenting your code. Because that in itself is a communication mechanism. And while you'll find, maybe in 2 years, you still can remember what you're doing. But when I go back to a code that I wrote 15 years ago, that hey, I found this old code. What is it doing? If I hadn't commented it, sometimes you're lazy and you have non-descriptive variables, and then you got to back reverse engineer. All it would have taken was a little comment just to describe what that variable was. You will find as you progress in the field that sometimes old algorithms, actually fairly often old algorithms, still work just perfectly well. They just run on new architectures and they tend to run faster than they used to. But the algorithm itself is good enough, or still sometimes even better than something you might write today.
Yeah,
So
absolutely.
keeping that library of old things. Problem solving, I think, is going to be a big thing because I guess you guys are familiar with debugging process. That is a major problem solving. So sometimes you really have to think outside the box because the computer tends to hide what's actually going on in the background. And so learning how to dive into the code and figure out why it's doing what it's doing because you put a plus sign instead of a minus sign. Because it'll still compile, it will still run, but it's not producing it all what you want. I can say think outside of the box. So this is one thing I look for a lot when I interview people for positions, because I want somebody who's not just good at programming or just isn't even just an expert in the field. I want somebody who can come up with crazy new ideas and new ways to do it. Because sometimes the new ideas, well, they might not be the best way to do something, but sometimes they're an entirely new way, a new novel way. And so even when you're going back to that debugging problem or trying to come up with a new solution to something new, you very often in the research world are going to have to think outside the box and come up with a way to do it. And sometimes you have to do it quick. Hard skills. I think nowadays most programming languages syntax is close enough that I don't really worry too much about whether you know C or Fortran or Python. I will tend to weigh C and Fortran maybe a little more than Python, because in the high performance computing world, they tend to perform a little better, sometimes a lot better than Python. And people who have generally worked in Python will tend to default to Python, whereas people in C and Fortran might be more willing to move up because they can see the advantage and ease of writing a small script to do something rather than a 20-page program that would do the same thing in 10 lines in Python. Also, I think people who, and this isn't, again, always true, people who write in C and Fortran have a more basic understanding of how the computer architecture is set up and how like, things like memory management works, which is important with what I do in high performance computing algorithm development. Do a lot of memory management and pipelining and so on. Again, it really depends on what I'm looking for, but having a breadth of that skill set. So coming back to my comment saying the programming language doesn't really matter. What matters more is the understanding of what that programming language is doing and what it's good at and what it's not good at. When you would use it, when you wouldn't use it. And I think that would be the most valuable thing to really learn and experiment with when you're writing these projects. Say, okay, I'm going to try to make it do this. Okay, I'm going to use a list. Okay, what if I got into TensorFlow in Python instead and I use one of their data structures? Or what if I tried a different data structure? How does the performance change? So experiment a little bit too. Like, don't just try the first thing and the first thing works. That's what you go with. You're doing your projects to learn as well. So.
Yeah, for sure. I can definitely like relate with that on a personal level because I believe it was last year I had to learn C# just for one project that I wanted to do. I think it was more on like the reinforcement learning game development side of things. So I had to like create a custom environment. And Python is not great at doing that. There are ways, but it's very inefficient. So I had to literally learn C#, which honestly isn't too bad. It's similar to Python. But yeah, definitely like exploring and finding new tools to help you achieve your goal is definitely worth doing. Okay.
The other side is programming aside, because computational material science is a multidisciplinary field. You also will have to have a decent, if not strong, mathematical background. If you're doing like a lot of finite element type simulations, you're going to be doing a lot of advanced linear algebra. If you do what I do, we do a lot of additionally like partial differential equations. We do a lot of model development, which just involves pen to paper doing math, or going to Maple or Mathematica using them somewhat. But you still have to understand the mathematical concepts to be able to do these derivations. And then you still need to have that understanding of the physics and material science, the thermodynamics, or the continuum mechanics, depending on your particular field, or even quantum mechanics if you're doing basic property calculations with DFT. So you have to have that understanding of quantum mechanical interactions. Molecular dynamics, you have to get into basic classical particle interactions. So depending on which area you're going to get into, you'll have to have at least some understanding of the physics.
At least regarding
Sure.
someone who's new to this industry, what is your opinion on exploring the post-undergraduate education in this industry?
I think a lot of, because you get the basics in undergrad, but I think having some post-undergraduate like master's or PhD would definitely help you get a position in a lot of these areas. Specifically, it really depends more so on what aspects, like what areas of the field you're going to get into. So like, for example, if you're going to do the quantum mechanical DFT, I think it's fairly common that they would require somebody with a PhD to move into even the industry to do that kind of research, to get that basic understanding. Things like finite element type simulations or fluid dynamic simulations, which are tied more to, say, mechanical engineering, but can often have materials impacts as well. Those are the ones that probably can get away with more of an undergraduate education. Although if you had a master's, it would tend to lend a little bit more. And what I think the postgraduate education gets you in these areas is you're interacting a little bit more and a little bit longer with experts in those fields. Because in a lot of cases, some of these fields are still research grade. Some of them are moving out of the research grade and more into the like an engineering grade tool, so like the fluid flow and mechanics simulations, but the DFT still is very much research tools, although it is moving a little bit out as well. Things like molecular dynamics tend probably not to really use it outside of the research environment. And then stuff like I'm doing, where I'm doing like mesoscale microstructure phase transformations, that too is probably still classified as research grade or more like understanding. There's no real commercial engineering. Well, that's not true. There is one. So I shouldn't say there's no. There is one commercial code out there, but it does take some expertise to run that. And I guess the other aspect would be like thermodynamic codes. The one that probably could get more in from just an undergraduate, surprisingly, is the newest area, which is kind of the machine learning and AI area. And that's probably less because they want that expertise, but because it's such a competitive market right now that they want people now. They don't want to wait 4 or 5 years to get the more higher expertise people, and there'll be a fewer people available for that, and the Facebooks and Googles out there will outcompete them anyway. So,
You know, for sure. And just to move on to like our next major topic, I'm gonna pass it on to Jeremy to discuss a few more neat things or interesting things about materials engineering and specifically under computational materials.
Yeah, so I kind of just like to know what's your favorite topic or area to research in computational materials.
I like efficiency. I am striving for real-time algorithms for practical applications. So like I could get real-time for like, to say, because as I mentioned, I do a lot of mesoscale microstructure type simulations. I want 3D and I want it to run in real time. But the problem is your microstructures tend to be on the order of millimeters to really get any interesting patterns, but your resolution you need are on the order of tens of nanometers. Maybe you can push it to hundreds of nanometers if you really push the models. So you're looking at 10,000 cubed in terms of mesh size. So my interest has really been, how do we push the bounds in terms of things like resolving where you need to resolve and just computing subsets of the volume you're interested in, but also how do you accelerate time? Because you know you're also, it's often the equations you're trying to solve could be very stiff, so you can result in small time steps. You can use some implicit techniques, either using finite difference, finite elements, spectral methods, whatever, to make your time step larger. You can still do it. So now the question is, okay, well, how do we use machine learning? Can we use machine learning to either become a surrogate for the model itself, basically learn from enough of the physics, and basically it supplants the simulation altogether, or can it do guesses? So then you go what we call like a high fidelity, low fidelity approach, where you basically, the machine learning model will say, okay, I've observed enough, I'm going to jump to here. Now you continue the simulation, then you jump to there. That still runs into efficiencies. So there's this thing called the Amdahl's law. Basically talks about efficiencies of parallel processing. Same thing applies here. So you're still tied to the underlying inefficiency of your model. I'm also looking, you mentioned reinforcement learning. So I'm looking at reinforcement learning to decide how to choose basically your local time stepping and your local mesh spacing, and allow it simultaneously within the same simulation, adjust the time step and mesh spacing here to run at a different time spacing and mesh there. But the complexity goes way up. So a human can never come up with a rule set, or be very pressed to come up with a rule set. So let's push it to reinforcement learning and see if reinforcement learning can learn what that rule set would be to make the decision as to adjust the time and spacing of the simulation. The other thing I've really been interested in now is, and I've actually been interested in AI a long time, And I think technology has caught up where it's kind of reinvigorated my interest, is in making decisions and drawing correlations between patterns. And this goes to some of the research we're doing at our lab in trying to design self-driving robotic labs. Mine is more broader. I don't care if it's a robot or not. A human could be running the experiment. We could be doing complete simulation, or we could have the robotic lab. But in the end, you could still feed the data you're generating into the AI system. And if it can draw correlations, and can it make intelligent decisions as to what experiment, simulation, or whatever next to achieve your goal, or whether that goal is to explore the parameters of space and just find new novel materials, or to make the best material for a particular application. So again, I'm kind of agnostic in where it's being applied. I'm just more interested in developing these better techniques to improve the overall efficiency. So I'm going to go with efficiency as my favorite thing in computational materials.
Well, that's definitely interesting. And kind of as a follow-up question, like how much more performance can you gain, would you say, generally speaking, by making these efficiency tweaks? Is it often like hundreds of times faster or thousands of times?
I try to target things that have the potential for an order of magnitude. So, for example, like the adaptive mesh that I built during my PhD, which was built on somebody else's adaptive mesh idea. And then when I say adaptive mesh, there are adaptive meshes out there, but this is really a dynamic adaptive mesh, in that in any given time, your mesh will have one structure, but then it's going to adjust its structure to co-move and evolve with the field that you're simulating, so that it can always maintain a certain level of error, or minimizing the error within the simulation. That will tend to reduce your simulation speed by roughly an order of magnitude, maybe 2, depending on the particular problem you're trying to solve. I then came up with another numerical technique, which I was using AI methods. Like so let me backtrack. So you could do, I'm giving you stuff that I haven't actually published yet. But so you go back a step, you try to do an implicit solution, because I typically in the past have run with explicit because it's just easy to program. But explicit you have to run with very small time steps, because numerical stability, your solution will explode and you get garbage results and not a numbers, and then it's not fun, you're sad, but then you're tied to a very small time step. So you go to an implicit solution, you can generally take arbitrarily large time steps. Not always true, but the time step you can take is often tied to not stability, but divergence from the real solution. So you have to still keep your time step manageable. Otherwise, your solution will just diverge from what the real solution is, even though it's stable. You're not getting not a numbers, but you are getting things there. The problem is the implicit solutions often will take interim iterations on the order that you would have had to have taken with the explicit time step. So I've developed a machine learning model which will look at the history of what has happened in the past during your simulation and do a guess as to what the next solution is going to be before it goes into the iterative process. So then you have to say, okay, what is my expected overhead to do this guessing versus what is the number of time step reduction I'm going to do. And so while my time step could be 2 or 3 orders of magnitude larger, my overhead to make that guess is probably an order or 2 higher. So you end up with an order of magnitude of 2 speed up rather than that. Then when I was talking about the reinforcement learning model, before I even considered it, I said, okay, what would it actually be doing and what would be solved? And so when we talk about solidification, which is what I'm targeting, is we get dendrites which grow. And so you have tips, which are very fast moving, and you got the sides of the dendrites, which are fairly slow moving. So the time step theoretically at the side of your dendrite could be an order of magnitude bigger than the time step of what's going on at your tip. So then you could do a volume ratio calculation, say how much of my volume at any given time is going to consist of tips and how much of my volume is going to consist of sides. Now this is very back of the envelope calculation, but at least gives you an idea of what you're worthwhile. And so when I did that calculation, it could be somewhere between 10 and 100 times volume ratio. In fact, it was like 98, 99% or something like that would be the sides, and then the other 1 to 5% maybe would be tips. Then you do your magical calculation, and based on saying, okay, if my time set is 10 times bigger or 20 times bigger, I think is what it was actually going to be. Then you could do a ratio calculation. You show, okay, this is in the order of magnitude, so maybe it's worthwhile to actually pursue. Then you go to the next step. You say, okay, now I need to prove a concept. Is my solution going to be stable? Because I don't even know. Like, yes, I could theoretically make time run at a different step here and here, but will my solution diverge or break just because of that? So then you start building small little proof of concepts. So I run mini simulations. You build 2 little domains, and you have your fields just kind of evolve through that and test out your system there. So it's really incremental development, proof of concept, but I generally always look for order of magnitude speed ups. Mind you, if it's a 50% improvement in speed, but it's only going to take me 20 minutes to do, I'm going to do that too. So it also scales with the amount of work that I have to do.
Yeah, thanks for your buck, definitely.
Yeah.
Well, that's awesome. So I'll pass it over to Kevin again to talk more about kind of like big ideas and the future of computational materials.
Yeah, so just to build upon what you mentioned, I believe you mentioned using reinforcement learning to help figure out a policy to choose different parameters. And that's like something you're doing currently. What do you think is going to be the application of AI within, say, the next 5 to 10 years in materials engineering?
There's a really big push around, there's I guess maybe 10, 15 years ago, a really big push for materials informatics, where they were trying to do what they call the Materials Genome Initiative in the US, which was akin to what they were doing in biology for the Genome Initiative. And that was really using data analytics to analyze and select within that, to optimize, find new drugs and so on. And then they said, okay, well, we should do the same thing in materials. So they started developing areas, databases. They were running codes to do simulation, develop data sets. There's been a lot of projects down in the US to build these databases. Another database that I use prolifically is it's a database in Japan called NIMS, where they collect a lot of thermodynamic data and publish that. Concept of organizing data really with like CalFAT approaches to develop thermodynamic systems. This is kind of had set, I think, the ground framework for which AI can really start to broaden in. And I think we're going to see AI in material science kind of go in 2 ways. One is going to be on production line. And this is pretty much going to be a given. In that they're going to have live sensor data. You're going to monitor sensor streams to see if whatever material you're making is going to deviate from its particular property. It's a question of which AI methods are going to be developed, what machine learning, it's going to happen. This will include image, watching the product line to see if something's deviating. Do you need to shut it down before something goes horribly wrong? In materials research, and I think that's another stream, is really about, I'm going to use the word democratize. So how are people going to develop these machine learning algorithms to help make decisions and do the data analytics to make decisions? And that's really what's tied to this materials acceleration robotic platforms. And I think there's going to be a large push for that. Whether something comes out of it or or not, because there are classical algorithms that you could also do to make decisions based on the data. There are downsides and upsides to using more classical optimization algorithms. The downside being you need to have an expert who's going to program all of the rules and do that. Whereas machine learning has this nice advantage that you can tend to let it figure it out on its own. One problem I have is that I know, and this ego talking, I know I can do it better if I take the time and do it. I can come up with a better rule set than I convince the machine learning will do. One is I don't have the time, and two, I might be wrong some of the time. So, but I'd say 90% of the time I'm convinced that I could come up with a better rule set than the machine learning model could.
Absolutely, because it's something that it's pretty deterministic, right? Yeah.
So the hard part for me is letting go and saying I'm going to try it, even though I think I can do it better, even though it will produce an answer faster if I do it myself, because it's a whole new research area. And that's a boundary that we have to get over in material science. Is right now it's a large leap to go from segmenting and finding a person in an image or a cat, as we traditionally do, to how do we go to this multi-scale problem that material science is and actually start applying these algorithms. And the problem is that's not where the money is right now. The money is in finding cats and people and other stuff and making these connections. What are you buying? And I'm going to connect it to this demographic, and that's what I'm going to post an image of in your ads on there. There's a lot of money there. Material science, not so much. But I think in terms of meeting our carbon emission targets, we need to start really looking at that. And that's where I'm kind of happy to be in government right now, because right now we are doing a huge push in kind of developing these methods to try to develop these materials technologies that are going to help us get to those carbon reduction targets. I'm talking like a commercial.
No, it's all good. Because yeah,
but
definitely. Sorry, go ahead.
I think the future, there is a future for AI. I think those are two main areas that you will see emerge. But I think it's still too early to really see where else it's going to show. Like, for example, they're already using it for, I'm going to say, more research grade stuff, like molecular dynamics. They use AI tools to learn interatomic potentials so that they can do classical molecular dynamic simulations, and they learn this from the quantum density functional calculations, and so that they can build the molecular dynamic kernels there. But really, AI to me is something that could take the place of a human to make decisions where it makes sense. So in an automated process where it might be too fast for a human to make the decision, or it's just getting too complex that we can just throw an AI model at it and have it make those decisions. So really, it comes down to decisions.
Yeah, for sure. And just to build upon that, is there anything in particular that you're surprised isn't being talked about more, specifically with the computational material science?
I don't think so. It depends on the community you're in. So, and depends on the field of material science you're in as well. I think there's going to be certain fields which are a little bit more reticent. For example, ones that have large capital investments, like say the steel industry, while they are interested in getting more into AI, they probably aren't really going to be invested in changing their entire capital run line to just because an AI will more likely work on it. Biomedical, I could definitely see maybe there's going to be some rigor around testing. And same thing with nuclear. So you could have an AI design the best material for usage in a nuclear reactor, but you're still probably going to have to go 20 or 30 years of testing to make sure that your reactor isn't going to melt down. So AI might discover it faster, but getting it to that particular application still has to go through separate rigorous testing. So it's a question of whether you can also trust the AI. Like, is it really making a decision? Because a lot of them, and I know some AI people don't like this, or like people saying it, but like, I'd say it is a lot of black box to it. And so really getting the inference. Now there's a lot of work being done, and there's a lot of people who can, you know, have developed ways to do the inference. But I think for the masses who are just going to, like, you know, PyTorch or TensorFlow and just using the applications, they don't have the expertise to do that dive down and really validate what the model has actually learned. And so while you can apply it to a method which will determine what I see as an advertisement, because it doesn't really impact anybody, like there's no safety or security. But if I did that same thing and blindly applied it to a new material in a car in the crumple zone, you might be a little less trusting of that without having a lot of rigorous testing done after that decision had actually been made.
Yeah, absolutely.
And so one big area, I guess going back to your question, is surprised not more talking about. I'd say people are talking about it, but I haven't seen a lot of good examples where this has been done well. And that's where you're tying the physics directly to the machine learning model. So it's basically almost like a hybrid machine learning physical model that can not just predict, but also co-explain what's happening. Once you have that co-explanation, then you get a level of trust. It's not just a random black box input and output.
Yeah, yeah. Okay, I just want to just quickly say thanks for answering these questions. Your answers have been very thorough, and I'll just like to pass that on to Jeremy to just wrap it up because we want to take the whole night today.
Yeah, no, definitely being mindful of the time. Thank you so much, Mike, for coming out and answering some of our questions. We really hope that this is going to help a lot of people who are like interested in computational materials and that sort of thing to get a better grasp of what's happening in the industry and what it's all about. So I'd say that concludes our little talk here.